Section 8.2, this is integration by parts. And this particular technique is used when other options aren't working. This is a very effective technique. What happens is you have a u, but you don't have the du. You have somebody else's derivative. And the rule says, and you can read in the textbook how it was developed, that it's u times v minus the integral of v times u. And many times when you do this, the v times u will integrate. So if we look at example 1, they want us to evaluate the integral of x e to the x dx. Now, the key on this, the first thing you look for is there one of the two functions that if you take the derivative, it goes to 1, or a number? In this case, it's the x. So I'm going to let the u be the x. And then the dv is going to be whatever's left. And now, I'm going to fill in the missing pieces. What's the derivative of u? It's 1 dx. And then go backwards. What's the integral of e to the x dx? It's e to the x. So now we're going to use the rule, and it says u times v. So x e to the x minus the integral of v du. And look what happened. I can integrate e to the x, whereas I couldn't integrate x e to the x. So this first part is finished, and the integral of e to the x is e to the x plus some constant c. The book kind of lays it out the same way, but this is the way I found it's the simplest to get. So now let's do it for x sine of x dx. This is example 2. And exactly the same thing happens. The x is going to disappear. So I'm going to let the thing that disappears be my u, and the thing that doesn't be my v. So du is just going to be dx. And if I integrate sine, I get negative cosine of x. Because the derivative of the cosine is negative sine, so the negatives would then cancel. So using the rule, it would be uv, so negative x cosine of x minus the integral of v du. Okay, with that minus can actually come out here and make that a plus. And now that's negative x cosine of x, and the integral of the cosine is the sine. And don't forget your plus your constant. Alright, so now, it's not always going to stay that easy. Part A in number 3 says evaluate the integral of x squared e to the x dx. Alright, so we start again, but we're going to do the same thing, but something strange happens here. We're going to have to do this more than once. So I'm going to pick my u, just like in example 1, to be the x, but now it's an x squared. And my dv is going to be e to the x dx. I picked the dv to be e to the x dx because no matter how many times you take the derivative of it, it's never going to go away. So its integral is e to the x. And the derivative of x squared is 2x dx. So using the rule, it would be uv minus the integral of v du. Alright, so now, the 2 is a number and it can just come to the outside. So I'm going to take an extra step here. Alright, so now the integral looks exactly the same as example 1. So we do the u dv technique again. U is x, dv is e to the x dx, v is e to the x, and du is dx. So I have all of this stuff sitting out here, minus 2. Now make a bracket because the whole integral, whatever you use on the rule, has to be multiplied by that negative 2. So the rule says uv minus the integral of v du, which then becomes x squared e to the x. I'm going to distribute the 2, x e to the x. That's going to be a plus 2 now, and the integral of e to the x is e to the x plus c. And it is, you can factor out an e to the x. The book did in this case. It's not really necessary, but if they want it completely factored, and then the plus c goes on the end. And the only reason you would do that is if you're trying to find max or mins, because you need to factor that x squared minus 2x plus 2 to see if there's a max or a min or a 0. Okay, before I go on to example 4, I want to show you something. This is not in your book, but this is a technique I've learned. We'll call it 3b. It's kind of 3b, but it's not. 3b is an n. The question is, what are you going to do if you have this? Because since x squared took us 2 shots at the u dv substitution, this one's going to take 3. And so if there had been any power up there, so they, in part B in the book they use an n there, and you're trying to figure out how to do it. There's a technique that's called, the integration by parts is called the tabular method. And what you do is you start out with u and dv, and you put under the u column the thing that you know you would pick as u, because if you keep taking its derivative it will eventually go away. So in this case it would take us 3 derivatives to do this, and probably 2/3 of a sheet of paper. And over here you put the dv. Now on the u column you take derivative, get down to 0. So the derivative is 3x squared, then it's 6x, then it's 6, then it's 0. Over here in the dv column you integrate until you line up with that 0. Well, this is a really easy one because the integral just keeps on going the same. Now, here's the tabular part. Draw the diagonal from the first u to the second dv, and go like that all the way down the page. The first one is going to be positive, and then it alternates. So now I'm going to write what I've got. The first diagonal says to me that I get x cubed e to the x, then I get minus 3x squared e to the x, then I get plus 6x e to the x, and then I get minus 6 e to the x, and then don't forget the plus c. That's what the answer would be if we did a UDV 3 times on that problem. Do you see it takes very little room? So this is a really neat technique. Now this technique only works if you've got a derivative that you can take down to 0. If it doesn't go away, this method won't work on.